I want to define the different kinds of Lie algebras. Now that you know what a Lie algebra is, what are the different kinds or different definitions, or we have to refine the idea of Lie algebras a little bit more. We are not talking about the classification of Lie algebras, we are talking about different kinds of Lie algebras. Let me tell you what I mean. So the first definition is a simple Lie group. Okay, so from the simple Lie group, we'll go to the simple Lie algebra, of course. So what is a simple Lie group? So a simple, do you remember what the definition of a simple group was for discrete case? Can someone remind me?
With a trivial center, probably.
Yeah, that's a consequence, yes. It was a group which doesn't have an invariant, a normal subgroup. Okay? So you can have a subgroup, but it cannot be a normal subgroup. So of course, if it has a abelian subgroup, then of course, abelian subgroups are by definition normal subgroups, right? And therefore, in abelian subgroups are centers, right? So, okay, so for Lie groups, a simple Lie group is a non-abelian Lie group that does not have a non-trivial, that is non-zero, a non-trivial normal Lie subgroup. You can have a subgroup, but it cannot be a normal subgroup. Remember, if H is a subgroup of G, it is normal if G of H is equals to H of G, right? For all G's. So that's what normal means. So this is H is normal. Another notation that I didn't use before, but I would like to introduce it now, is that a lot of times we call normal subgroups invariant subgroups, okay? So a lot of times, you'll find that normal subgroups are the same as, okay, I should not use the mathematics notation. Normal subgroups are also called invariant subgroups. Okay, so a simple Lie group is a Lie group which does not have a normal, a simple Lie group is a non-abelian Lie group which does not have a non-trivial normal subgroup. Okay, so now let's make a couple of comments. So a simple Lie group may have discrete normal subgroups, okay? May have discrete normal subgroups. And that's actually very normal to have. Okay. Sorry. So for example, we know that Z2 is a subgroup of SU2, right? Because Z2 is just generated by the 2x2 identity matrix, which is of course an element of SU2, as well as minus of the identity matrix, right? And all of these matrices, because they're diagonal matrices, they commute with all the elements of SU2, right? So, and therefore they're an abelian subgroup, and therefore they're normal subgroups, right? But they are not Lie groups. But Z2 is not a Lie group, right? So in fact, SU2 has an infinite number of discrete normal subgroup, because all the Zn groups are subgroups of SU2, right? So these are essentially matrices which are of the form of, if you take the e to the power I 2 pi k over, say, n, and then 0, 0 e to the power minus 2 pi I k over n. Sorry. So all these elements, they form a group, and they are essentially for discrete k's. So k goes from 0 to n minus 1, right? So these are they generate the Zn groups, right?
It's
Okay,
because
so
the nth roots of unity forms a group, and we're just making a matrix representation of it.
yeah, exactly, yeah. But this is a normal subgroup. That's the point. But it's not a Lie group.
Yeah,
It's
K
not
is discrete.
Yeah. Okay. So the other thing is that yeah, the second comment is kind of trivial, but so a Lie group, a simple Lie group, gives rise, arises from a simple Lie algebra, which we'll define below. Simple Lie algebra, which we shall define below. Okay, so, but before we define a simple Lie algebra, let us define an invariant subalgebra. So the definition of an invariant subalgebra. So, suppose that G tilde is a Lie algebra, and K tilde is some subset, okay? Now, K tilde is an invariant subalgebra if commutators of the elements of K tilde with the elements of G tilde either results in K tilde or 0. Okay, so if this is the case, then K tilde is an invariant subalgebra. Okay, so basically, you have, so this is say G tilde and K tilde is some subset. And the commutator of an element from say K tilde and an element say from G tilde takes you back into K tilde. Okay, so the combination of these two things takes you back to K tilde or to 0. Okay, so then we call that an invariant. K tilde is an invariant subalgebra.
Sir, is it redundant to write K tilde or 0? Like, I was wondering whether 0 should belong to K tilde as well.
So K tilde is, no, it is not redundant. It's, so it's basically, if for all of the K tildes, if this is the case for all of, for all the cases, right? I mean, or, oh, you mean whether 0 should be an element of K tilde? No, K tilde is a, we are not, when we're talking about the Lie algebra, we are really not talking about, I mean, it is
because,
there.
Yeah, 0 can be represented that way.
Yeah, so, yeah. Okay. All right, so, so now we are ready to define a simple Lie algebra. Okay, so if a Lie algebra has no non-trivial invariants of algebra, then it is a simple Lie algebra. Okay. So let's give an example. The Lie algebra of SU2. So SU2 consists of 3 generators, T1, tau 1 and tau 2 and tau 3. And, we have the commutator of tau I and tau j is I epsilon I j k tau k. Or say tau 1, tau 2 commutator is I, tau 3, etc., right? So we see that, there is, say, no subalgebra, say, if I take just one of these guys, when we commute it with another one, it doesn't close in on itself, right? So T1, T2, if this was, say, some linear combination of, say, T1 and T2, so, then we would start having a Lie algebra which was not simple. Okay, in this case, it is simple because we see that this structure is not realized.